Hi, I'm Hamilton, doing it the Kiwi way. And now we're doing our cMOS NAND gate. First the equation, Q is equal to A and B, the truth table, inputs A and inputs B, result Q. The inputs 0, 0, 0, 1, 1, 0, and 1, 1. When A and B are both 1, the result is 1, or try, and the rest is 0 here. The AND gate is represented by this. Result Q with inputs A and B. Let's do we'll do the nMOS representation first. We have our VDD, we have our resistor, and have our two inputs, A and B, and out comes our interim result. We'll call that C. Then we have another VDD here, our resistor, and that all goes off to ground. Our transistor here, and out pops our result here, Q. Just label that resistor, and the resistors will set at 220 ohms. So the Qn, which is this part here, is equal to A and B all knotted. This is our knot or inverter, and the A and B, we've got A and B here in series. Now let's do our cMOS of this. So we have our VDD here, in here. Our QP is the complement of A and B all knotted. ANDs becomes ORs, and we'll keep our knot sign up here. We replace the resistor with the QP. ORs are in parallel. Put a circle in there. This is input B. This is input A. And that is our QP, except with a knot. And then we do our pull down network. And that's off the ground. We have our inputs A and B again. Our result here is our interim result C. I'll call it C, you can call it anything you like. And then we need to do the knot. So we have another VDD here. Replace the resistor with the equivalent pull up, which is this. And then we have our pull down. Then we go off the ground with our result Q here. What we'll do is just label our gates and drains and sources. We've got drain here, source here, source here. We've got our gates. we've got a gate here, we've got a drain and source. For cMOS, the PMOSs, we've got our gates, we've got our sources and drains, and down here we've got our drains and sources with our gates, and up here we've got our source and drain and gate, and now we've got our drain and source and gate. I think that about covers it off. I'm just quickly checking. Whoops, we forgot a circle here. Show it's a PMOS. That's good. So now we'll go and implement that in Multisim. Excuse that squeaking, that's my chair. Right, we're in Multisim and we've got our previous example open, nMOS NAND. So I'll save that. And go cMOS and we'll save that one, or rename it to cMOS NAND, sorry. cMOS and Elvis. May not be using this, may take too much time. In fact, we'll close that down now. Right, I'll speed things up a little bit and then I'll explain what's happening. Right, that's about done. It's reasonably tidy. We'll go back to our configuration here. We've got interim result C, we've got inputs A and B. Going to our pull up area. Just label that one pull up actually. Pull up network. We've got our pull down network here. And here we've got our pull up again. And here we've got our pull down network. Our equation is correct, so let's go and quickly look here. So we've got our resistors as before for our switches required to not short circuit the battery. And this is our pull-up network here with PMOSs. This is our pull-down network here with our nMOSs. Our interim result C goes here and goes into our inverter, and the answer Q pops out to drive the LED display. When both switches are open, 5 volts are applied at the gate, which is 1 and a 1. We get an inverse version here, which is a 0, and then we invert that and we get our 5 volts here, and the 5 volts displays the LED. 5 volts being a 1, here's a 0, and here's a 1 and a 1. When we close this gate here, we apply a 0 and a 1. We get a low voltage, very, very low voltage here, and the LED is off. When we close this switch here, is a 0 and 0. We apply a 1 here, and we'll pop out a 0 here, and the 0 is LED off. And we can do that in the other situations as well. So now let's go and implement that on the breadboard. So what we've got here is our 2 PMOSs. This configuration is our nMOS NAND gate. We're going to replace this resistor with equivalent pull-up using our 2 PMOSs here. Then we're going to connect it up to our existing inverter, and that's in cMOS configuration. We haven't got it connected yet, the red wire is disconnected, and that'll drive at the end of the day our answer here. So what I'll do now is I'll speed things up and see how we go. So a quick summary here, we'll just apply 0 volts, 5 volts because the button's not pressed. Show it on the digital multimeter. Right, we've got almost 5 volts applied at this gate. And the button's not pressed on B either, so we've got almost 5 volts here, which is equivalent to a 1, 1 and a 1, and equals LED on, which it is on here. Press both buttons down, we're getting 0 volts on both gates. 0 and 0 equals 0. Very little voltage. 0 and 0 is the LED off. We have the top button in the open state and the bottom button in the closed state. Our multimeter's recording button B at the moment, and it's got 0 volts. And if we look at the top button's in the closed state. I mean open state, and the bottom button's in the closed state, sorry. And we've got 5 volts being applied to the top here, as you can see. 1 and a 0 equals 0. Our LED should be off, which it is in this case. Again, release both buttons. LED is on. We've got 5 volts applied at A and 5 volts applied at B. And we look at our answer way over here, should be 5 volts or a 1. Which it is. And then we go through our load circuit, which is our nMOS and our PMOS to drive the LED, and we've got a resistor down here. I think that's about it.